Lectures for Chapter 17. This is Buffers Part 1. We're going to walk through definitions. I've tried to break them up into little chunks so that you could rewatch particular sections and not have to rewatch the entire chapter if you just wanted to look at one thing. Okay, so we're going to do definitions first. First thing we've got is buffers in the common ion effect. So what we've done up to this point is that we've done the weak acid. Okay, we did the weak acid, no problem. But now we're going to add our weak acid, been here, done this. But now we're going to add the common ion, so aka the salt of either the conjugate acid or the conjugate base, whichever one is appropriate. And what happens when you do this is you have Le Chatelier's pinch pull at work. So it's still going to shift to the product side, but it's not going to shift as far. So you're going to have less shift to product side. Now, why is that important? Because H plus would be less, which means our pH is not going to change much because you've got the shift going back and forth. Okay? So, if we're looking at this, the way this works, and I've already pre-started this because, for time's sake again, the A is strictly a weak system, weak acid. You know how to do that. You set up the ICE table. You set up the Ka. The Ka here is given. And you solve for the hydronium ion concentration. And so you're going to end up with a pH indicating about 1.98. Now, looking at the percent ionization, and we didn't ask for that, but a lot of times you can look and see what is happening based upon the percent ionization. So it's there. Well, that means when we go to part B, where we have the common ion, so this is the buffer, we have both HNO2 and we have NO2 minus. Okay, so what that means is we set up our K value, and because we know that our ionization is going to be less than what we had originally, and that was only 0.72, we can make the assumption that dissociation is minimal, which means the hydronium ion concentration won't change much. So if you do this, then you end up with X times 0.10 divided by 0.16, again, is equal to the Ka, which is 7.2 times 10 to the minus 4. Do the math. X is equal to 0.00115 molar, which is the H plus concentration. Now, this percent ionization is not right. I apologize, screwed that up. Don't want to have to redo this whole thing. So it is going to be much greater than that, because what I find is 0.001152 divided by 0.016 times 100% is going to be equal to 0.72%. Okay, I will go back, rework the percentage, and re-put it in there in the final value, or I'll try. But it's going to be greater than that. So bottom line is, with the common ion, we're less than 1%. So our assumption is valid. So we're good here. Now notice if we take the negative log here, our pH for this value is 2.939 or 2.94. So if you'll notice, we have an entire pH unit adjusted between what we would have with the pure weak acid and when we add the common ion. So we've moved an entire pH unit up, which means we've become much less acidic. So, and this is for a relatively strong weak acid. If you have a weak acid, then the variation will be even more intense. Okay, So what happens is that the common ion then creates the buffer. Because the equilibrium does not change, the pH is not affected. So basically, this is what makes a buffer important. It resists extreme changes in pH. Now, this is crucial. Your body is a whole system of buffers. For example, if we take your stomach makes acid way down below one pH of 1. It's very, very, very acidic. Well, if you were to dump that on your skin, it would burn it. And it's even worse internally. So what happens is when your stomach acid dumps into your intestine, then that immediately buffers it so that it can handle the extreme change in pH and not basically kill you. So when you get to biology, they're going to talk about buffers a lot, and there are any variety of them in the body. But what you must remember is regardless of where you're using the buffer, it has to be a weak and its conjugate. Okay? So we'll work one more problem and then we'll look at some specifically on how buffers are made or species involved in buffers. Okay? So one of the buffers, as I said, is a blood buffer. And we're going to prepare a liter of buffer containing 0.025 mole carbonic acid and hydrogen carbonate ion. Okay, so that means carbonic acid is H2CO3 and it's dissociating to H plus HCO3 minus. So we have initially, we have 0.025 molar there. And we have 0.0025 molar here. Now, these were both given in moles, but it's per 1 liter, so the molarity is needed. And in each case, because you're doing it over 1 liter, it comes out to be the same as the moles. So you do have to pay attention to that as we go. But in this case, so our change, we're going to shift to the product side. We have to, because we have no H plus. So it's 0.0025 minus X, and 0.025 plus X. So again, your Ka value would be equal to 0.025 plus X times X divided by 0.0025 minus X. And your Ka value is 4.4 times 10 to the minus 7th. Remember, you can get those off the table. And since we've got more of the product than we have the reactant, we're going to assume minimal dissociation. So we end up with getting rid of this X and this X. So we end up with 0.025 over 0.0025. This one's got the X is 4.4 times 10 to the minus 7th. So X is 4.4 times 10 to the minus 8th, which is the hydronium ion concentration. Take the negative log of that, so your pH is equal to 7.3565, so it's 7.36 is your pH. So if you'll notice that carbonic acid keeps the blood slightly, not much, but slightly basic. Okay? If you're a visual person and you want to look at this, what basically happens is in a buffered solution, we're going to start with our acid or our conjugate, or our base and our conjugate being comparable. And so if we add hydroxide, we're going to produce the conjugate base. If we produce H plus, we're going to produce more of the acid, the weak acid. So this is your visual, and again, basically it's the same thing as we did before with Le Chatelet's principle, except now it's specific for pH. Okay, so if you look at this, and normally we would run this in lab, we will be doing a lab. You will find it posted as a quiz in your lab section. But I want you to look at these two buffers. We've got the buffer 1 and buffer 2. Notice the only difference is concentration. So for this buffer, we stay buffer, 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 buffer. We're still buffered. Here is where we break the buffer. Okay. If you're more than 1 pH unit off, your buffer is broken. That's the technical definition. If you're just trying quick and dirty, you just kill either all of the weak acid or all the weak base. It doesn't matter. Now on this next one, we keep buffer, 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 and we still haven't broken it, so we didn't break it. So what's the difference is this one is 0.2 molar and this one's 0.01 molar. So what does that mean? Okay, because a buffer consists of a weak acid and its conjugate base, or weak base and its conjugate acid, it's going to resist changes when small amounts of acid and base. Okay, because what it's really doing is, and I'm going to jump forward to buffer capacity and then I'm going to come back. Okay, the ability of the buffer to retard changes in pH when you add small amounts of strong acid and bases. Okay. Now, the greater the amount of weak acid and conjugate base present, the more can be neutralized. Okay, well, we did this previously, but so if we look at solution 1 and solution 2, this one's 1 molar and this one's 0.5 molar. So basically, this one has more acid conjugate base. This one has less. So think of it this way. If it has more, it can absorb more. So we say that buffer capacity increases with increasing concentration. So when you have a buffer that's really strong, then it will hold a whole lot more than if it has less. Okay, so let's go back to the ones we skipped. Okay, back to this one. We said what buffer capacity was. Now let's talk more about how a buffer actually works and what we can use with it. Okay, so it has to be a weak acid and its salt, or a weak base and its salt. Now, here's the tricky part. The salt can either be added, for example, as a group 1, so like sodium A, etc. Or if you take a weak acid and add a strong base to it, the net effect is you create the A minus plus water, which, has no effect. So in the case of a weak base, if you take the base and add a strong acid, then you get the BH plus. So the net effect is we need HA and A minus. Here we need B and BH plus. The weak acid or base is given. The salt can be generated one of two ways. So if we look at these sets, the question is identify the buffer systems in the following. So the easiest thing to do with this is to identify what we have. So this is a strong acid. This is a weak base. So assuming we don't use up all the weak base, the strong acid plus the weak base produces the conjugate, H2NNH3 plus. So if we have this and this present, this is the weak base and this is its conjugate acid. So is this a buffer? Yes, this one is. Okay, so let's go down here. So this one is NH4 plus, and this one's HCN. So this is the conjugate acid of a weak base, and this is a weak acid. Okay, a conjugate acid and an acid are both acids, so this cannot be a buffer. Okay, so if we look at the next one, this is a weak acid, and this one is group 1, which means this one is a salt. So it's going to dissociate into that. So notice that this is the conjugate base of this weak acid. So, yep, this one's a buffer. We have the acid as conjugate base. Over here, this is a strong base. This is a strong acid. Two strongs do not make a buffer. Okay, this is a strong base. This is a weak acid. So if our strong base reacts with our weak acid, we produce F minus plus H2O, which means that if we look at this pair, we have our weak acid plus our conjugate base. So are we a buffer? Yes. Okay. Again, if we look at this, this is a halide. So this means this critter is again a salt, which means it's going to dissociate into HONH3 plus the halide up here, which we don't care about because it's counter ion. And this is a weak base. So look here. This is the conjugate acid, and it happens to be the conjugate acid of this weak base, so the answer is yes. Okay? If you have a conjugate of not the acid or base that you have, then the answer is no. We have to have both species involved to set up the equilibrium. So you may be asked to identify which or is the following pair an acid base buffer. Okay? Now, we're back to what happens when you add the strong acid or strong base to the buffer. We've got to normalize it. Well, how do we do that? Okay? Well, the first thing we've got to do is look at what's going on. Because remember, when you're looking at an equilibrium here with a weak acid, this is really what it is. So, the question is if we're going to add HCl, which is the strong acid, that really is going to dissociate into only H+. Well, H+ is an acid. It's going to react with the base form to produce more HNO2. So there's where your shift is. So what happens when you add a strong acid is you produce more weak acid. Okay, flip side of it is, if we add sodium hydroxide, it's going to dissociate into sodium ion plus the hydroxide. Okay, so that means that the hydroxide is going to react with the acid, because this is the base form. So the acid form is HNO2, so this is the acid form, to produce more of the NO2 minus, the conjugate base. So the net effect is the strong base produces more of the conjugate base. Okay, that's in a weak acid. In a weak base, it's pretty much going to do the same thing except in reverse. So again, strong acid, we get H+, it's going to react with the base form, which is HONH2, because remember, this equilibrium involves the weak base plus HONH3 plus OH minus. So it's going to produce more of the HONH3 plus. So what we did was more conjugate acid. Okay, so the strong base, and again this is a weak base, so it's the hydroxide, and it's going to react with the acid form, so it's going to react with the conjugate acid, which is HONH3 plus, to produce HONH2 plus H2O. So this is the base form. It's the weak base form. So we're producing more of the weak base. So the net effect is kind of like the leveling effect we did in chapter 16. The strong acid is converted to whatever the weak form is in the buffer. The strong base is converted to whatever the base form is in the buffer. And this is how the buffers work to minimize pH changes. Now, here are a variety of buffer systems. And so if for some reason you needed a buffer at about pH of 4, you'd probably want to use lactic acid. But if you needed one about 9, you'd want it down here at ammonium. So you can pick, and the list of buffers possible is tremendous. And in biology, you'll get into MOPS and TRIS and all kinds of lettering that stands for any variety of buffers. So as you get up in the biology and you encounter these, it works exactly the same way. It's just a more complicated molecule, but it's still just who's got the proton. Okay, so again, we've already covered buffer capacity, so we're done.